Great work! In the previous tasks, you have been familiarized with maximin and minimax strategies. In this task, I'll teach you the solution concept of Nash equilibrium. Please switch to the sheet Nash equilibrium. By definition, at this equilibrium point, none of the players will have any incentive to deviate from it. That is, to arrive at this equilibrium point, we need to consider the opponent's strategy and figure out the optimal solution. But we need to keep in mind that a game may have one or even more Nash equilibria. In some cases, there might be no Nash equilibrium at all. We will consider this 2 by 2 matrix. We will use these colored arrows at the bottom of the matrix for the ease of understanding. The blue arrows are for player 1 and the green arrows are for player 2. The arrowheads are used to indicate the intention of a player to move from one strategy to another strategy with better payoff by fixing the opponent's one strategy at a time, and repeat this process for each of the opponent's strategies. I know, it sounds complex, but it is very simple to work it out. I will illustrate the process with this 2 by 2 matrix. Consider player 1 thinking player 2 plays A. What is the best strategy can he employ? Look at the payoffs for player 1 in the first column. These are 8 and 15. Since 8 is less than 15, therefore, it is beneficial for player 1 to play B when player 2 plays A. So we put the arrowhead from 8 to the direction of 15. Similarly, if player 2 plays B, player 1 is better off by playing B as well, since 3 is greater than 1. So the arrow moves downwards. We will repeat the same process for player 2. Considering player 1 will play A, player 2 will choose B, as 8 is less than 15 and the arrowhead points at 15. Again, if player 1 plays B, then player 2 will choose B as well, and the arrowhead will point at 3 since 3 is greater than 1. Now combining both player 1 and 2's decisions, we will look for a combination where the arrowheads of both players coincide, that is, a blue arrowhead and a green arrowhead coinciding. In this case, only the fourth quadrant has both the arrowheads, and therefore is the Nash equilibrium point for this payoff matrix. I hope the method is now clear with you. I have a mini task that you could try out on your own. Please scroll down a bit. You will see another 2 by 2 matrix. You can pause the video and try it out before we move forward. Okay, good job. Now let's find out the Nash equilibrium together. As you have noticed, the payoffs are in negative. So the motive would be to incur as much less of a loss as possible. We will begin with player 1. Considering player 2 chooses to play D, player 1 is better off playing D, as -3 is less than -4 in terms of loss. Again, if player 2 shifts to C, then player 1 is still better off playing D. Similarly, for player 2, if player 1 plays either D or C, it is always better to play D. Therefore, combining their choices, the final solution is D and D, that is, -3 and -3. This matrix is the example of the classical prisoner's dilemma problem. In the next section, we will solve this problem using the template.